Assalamu alaikum students. I hope you all are fine. I'm your teacher Sumayya Khan, and today students we are going to study about the transition and inner transition elements. We have started this chapter and we have already done what is meant by transition elements, what is the position of transition element in the periodic table, which elements would be termed as transition elements and which elements would be called inner transition elements, that is D and F block elements. We have discussed that. We have also discussed about the electronic configuration of the D block elements. Today students we are going to study about an important feature of the transition element, which is variable oxidation states. Okay, you'll find that we'll discuss only about the 3D series in detail, but in general students when you analyze about the oxidation states of transition elements, you will find that most of the transition element shows more than one type of oxidation state. Here in this picture you can see 3D series of first transition series is mentioned here, along with the oxidation states shown by these elements. Only scandium and zinc are the two elements which have or which shows only single oxidation state, whereas all the remaining elements are capable of exhibiting more than one type of oxidation states. So when you move from scandium to zinc, when you reach in the middle of the series, that is at manganese, you will find that the manganese shows the maximum number of oxidation states, and after manganese when you move forward, the number of oxidation states goes on decreasing. Now the reason for showing these multiple number of oxidation states is the presence or participation of electron that are present in 4s orbital as well as in 3d orbitals. The energy gap between 4s and 3d orbital is very less, or you can say they are almost similar. So when this happens, when the electrons are removed, then only the plus oxidation state is acquired. Okay, so whenever the electrons are lost or removed, they are always lost from the outermost shell, which in this case is your 4s orbital, and it can only accommodate 2 electrons. Okay, that is why the least number of oxidation state you will observe here is 2, and somewhere you will also find plus 1. The reason I will tell you later. Okay, now the electrons are firstly removed from your 4s orbital, and after that the d electrons can also be lost or can be shared. It is not necessary that the electrons are always lost, that is these metals are going for only ionic bonding. They can also go for covalent bonding. So these electrons which are lost or shared, these electrons can belong to your s orbital as well as your d orbitals. Okay, now here I have mentioned the reasons. Okay, we know that transition elements show oxidation, different oxidation states, and this is due to what? The atom can lose different number of electrons. If the element is showing only one type of oxidation state, for example let's say scandium shows +3 oxidation state, it means that it can either lost or share 3 electrons, or it cannot share or lose any 1 electron or 2 electron. Okay, any other number of electrons cannot be shared or lost by the scandium. Okay, it can only share 3 electrons. Okay, but most of the other elements can share different number of electrons. Okay, this is the reason. And the second thing is why this is possible, that the element is showing more than one type of oxidation state, because both s orbital as well as n minus 1 d subshell orbital, these orbitals are involved in the bonding. Their energies are same, so electrons from these orbitals can be lost or shared. Okay, the lower oxidation is generally shown when only s electron participate, whereas higher oxidation is shown when both s as well as d orbital electrons participate in the bonding. Okay, let's see an example of vanadium. The ground state electronic configuration of vanadium is shown here. Okay, till organ 18, we know how to write the electronic configuration. We are concerned about the outermost electronic configuration, which is 3d3 and 4s2. I have shown you the orbitals of d and s orbitals containing the electrons in it. Okay, so your 4s has 2 electrons and 3d have 3 electrons. When vanadium can show 4 different type of oxidation states, +2, +3, +4 and +5. Here I have shown only 3. Okay, so when vanadium is exhibiting +2 oxidation states, you should understand the electrons should be removed from the outermost 4s orbital. Similarly, when it is showing +3 oxidation state, the first 2 electrons are removed from your s orbital and then 1 electron is removed from the d orbital. So your 3d contains only or left with only 2 electrons. In the same way, if it is in +4 oxidation state, you know how to write the oxidation this thing electronic configuration. 4s will again contain nothing in it, and your 3d will be left with only 1 electron in it. Okay, that is 3d1 4s0. In +5 oxidation state, all the electrons from s and as well as d are lost. Okay, so you know how or why these variable oxidation states are possible, because the electrons from s as well as from d orbitals are able to participate in the bonding. Okay, in the same way, students, you can show the variable oxidation state of any elements. Now the question is asked, which of the first transition series element shows the maximum number of oxidation states and why? And after answering this, we'll answer which elements in the 4d and 5d series will show maximum number of oxidation states. Students, when you'll analyze the variable oxidation states of all the transition element, you will find that there are some element in each row which will exhibit maximum number of possible oxidation states, and these element you'll find will come approximately in the center of the series. So let's see the first series, that is your 3d series. In 3d series, manganese is the element with the maximum number of oxidation state. I have shown here the electronic configuration of manganese in ground state. You can see here manganese have 2 electrons in s orbital and 5 unpaired electrons in d orbital. So when electrons are in the unpaired state, their uh, chances of participation in bonding are more. Okay, so you can see here the manganese exhibits 6 different types of oxidation state ranging from +2 to +7. Out of these 6, +2 and +7 are the most common oxidation states of manganese. So you have given the answer that manganese show maximum number of oxidation state. The reason is that the electrons that are present in s orbital as well as in d orbitals are able to participate in bonding, and it has maximum 7 electrons in its outermost and penultimate shell. Therefore, it shows maximum number of what uh, oxidation state. Now after manganese, students, what will happen, your electrons are going to get paired up in the d orbital. For example, if you will take the iron, the configuration will become 4s2 3d6, and you will add one electron in the first d orbital and it will pair up. Okay, so when the electron starts pairing up, the number of this thing unpaired electrons starts reducing in the d orbital, and the participation of these unpaired electrons or the electrons present in the d orbital in the bonding becomes less. Okay, in the same way, in 4d series you will find that ruthenium exhibits maximum number of oxidation state, and in 5d series rhenium shows maximum number of oxidation state. Ruthenium shows 7 oxidation states and rhenium shows 8 oxidation states. Here I have underlined some oxidation states with the red line, which means that the red lines means here that these oxidation states are uncommon. Okay, these are not generally shown, but it can show these oxidation states also. Okay, so these are the red light oxidation states are uncommon oxidation states of these elements. Okay, now another question is asked, write the electronic configuration of ions manganese 6 plus, manganese 4 plus, iron 4 plus, cobalt 4 plus, nickel plus 2. Now whenever this kind of question is asked, students, the first thing first, you should know the name and atomic number of these elements. Okay, so Mn is your manganese and its atomic number is 25. If we know the atomic number, we can easily write the electronic configuration. The ground state configuration is shown here, organ 18, 3d5, 4s2. Manganese plus 6 means that manganese in neutral state has lost 6 electrons. Okay, now manganese is in ionic state. Mn plus 6 is an ion. Okay, so how the 6 electrons are lost? So first you just remove 2 electrons from your s orbital and 4 from your d orbital. 6 electrons are there. Okay, so you are left with only 1 electron in your d orbital and no electrons in the s orbital. So you will write organ 18 3d1. If you are not writing 4s0, then also it is correct. Okay, Mn plus 4 means loss of 4 electron. It means that 4 electrons are lost by the neutral manganese. So 2 are lost from, obviously, from the outermost 4s subshell, and then 2 more are lost from your d subshell. So you are left with 3d3 4s0. Similarly, students, you can write the electronic configuration of iron, cobalt and nickel ion. Okay, so write their electronic configuration first, always first in the ground state, and then from the oxidation state or oxidation number of the ions, you can find out that these many electrons are being lost by these elements. So you remove these number of electrons from the ground state configuration of your element. Always remember, first you will remove the electron from the outermost shell, that is your fourth shell or the principal shell, whichever it is, and then you will move into the penultimate d shell, n-1 d shell, and remove the number of electrons that are required by the oxidation number of your element. Understood? Another question is here, name a transition element which does not exhibit variable oxidation state. You can see the answer is already presented here, scandium 21. But before just writing the answer, we should also able to know why we are saying that scandium is the transition element with only single oxidation states. Here we are talking about basically we are talking about the 3d series, the first transition series. Okay, So if you had remember what are the oxidation states, you must have observed that in your 3D series, scandium and zinc were the two elements with only single oxidation state. Scandium had +3 oxidation state and zinc exhibit +2 oxidation state. So these were the two elements in the 3D series with only single oxidation states. But why we are saying scandium is the element which is having only single oxidation state? Because the question is not to name the elements that belongs to D block, but to name the transition element that have only single oxidation state. So we know that zinc is not a transition element because it does not have incompletely filled d orbital. The d orbital in zinc in its neutral atom state as well as in ionic state is completely filled. It has 10 electron in its d orbital. So for being a transition element, the element must possess incompletely filled d orbitals. That is, it should have the number of electron in d orbitals will range from 1 to 9. Okay, so if any of the element is having from 1 to 9 electrons in its d orbital, penultimate d orbital, it is transition element, otherwise it is not. Okay, so scandium is the transition element that have only single oxidation state, which is +3. Okay, and why zinc is not? Because it is not a transition element, though it belongs to D block, but not a transition element. Okay, now let's see. I've told you that the lowest oxidation state shown by the 3D series is +1. Okay, now if you have remembered that while discussing the electronic configuration of 3D series, we have emphasized especially on the configuration of two elements, chromium and copper. Okay, because chromium and copper does not show the expected electronic configuration. They show some exceptional behavior, where you observe that in case of copper, instead of showing 3D9 4s2 configuration, copper shows 3D10 4s1 configuration due to the extra stability that can be attained because of the completely filled and exactly half filled orbitals. Okay, so here in your 4s orbital, which is your outermost orbital, there is only one electron. So copper in +1 oxidation state, when it loses only single electron, you will find what? Copper in +1 oxidation state by losing that electron which is present in outer 4s orbital. Understood? So out of all the 10 elements of the 3D series, copper is the only element which will exhibit +1 oxidation state, which is the lowest oxidation state in 3D series. Hope you have understood it. Now let's move forward to next topic, which is physical properties of first transition series. Look, transition elements show all the characteristic of the metals. We know what are the general characteristics shown by all the metals. All metals we find are hard, generally hard. They are lustrous, malleable, ductile, good conductor of heat and electricity. It can form alloys with other metals. It exhibits high melting and boiling point, and have one or more typical metallic structure, that is BBC, HCP, like this. Okay, so all these are what comes under the physical properties of the first transition series. Now this is an important topic, trends in atomic properties of the first transition series. Here we are going to study about the different properties of the first transition series. Okay, and we are studying trends, so we are going to observe that how these properties changes across the series. It is very fortunate, you are very fortunate that you are just studying about the 3D series and you are not studying all the 4D, 5D and 6D, all the remaining series. Okay, so we'll emphasize only on the 3D series, but you will observe these behaviors are general. Okay, now here in the table you can see the 3D series along with its atomic radii. Okay, and you can observe that from scandium to zinc the atomic radii is decreasing from 164 to 137. You will observe the gradual decrease in the atomic size from scandium to chromium. Okay, and after that you will find that uh, from iron to copper the atomic sizes nearly become constant. Okay, iron, copper, nickel, iron, cobalt, nickel, copper, they will show what, almost no change in their atomic radii. It is almost constant, and then there will be increase in the atomic size in the zinc. So in general you can say the atomic and ionic radii of transition series decreases gradually from left to right, that is from scandium to zinc. And this is happening because whenever atomic number, look, atomic number is increases by 1, from scandium is 21, then titanium is 22, like that. So atomic number is increases by 1. Okay, when we move from left to right, when the atomic number increases, it means the effective nuclear charge is also increases. The effective nuclear charge is responsible for the attraction of the outer electron with the nucleus. Look, the positive charge in an atom is concentrated in the center, okay, which is nucleus, but the electrons are dispersed around the nucleus. The negative charges are dispersed around the nucleus, and this central positive nucleus have attraction with these negatively charged electrons. Okay, and these electrons are present in particular shells, first shell, second shell, third shell. Okay, so if you want to find out what is the effective nuclear charge experienced by any electron in a particular shell, you can calculate it easily with the help of the formula of effective nuclear charge. Okay, but in general keep in mind it is the force of electrostatic attraction between the central nucleus and the negatively charged electron. Okay, and this attraction depends upon in which shell your electron is present. Okay, so when the this thing atomic number increases, the effective nuclear charge also increases, and the outermost electron will experience more attraction with the center. Okay, now due to the more attraction between the nucleus and the electron, the size of atomic atom starts reducing because the center, the nucleus, is pulling the electron towards itself. Okay, so this is what we observe from scandium to chromium. But after that you will observe there is a constant, almost constant size of this thing, atomic radii, even though the effective nuclear charge is reducing. Now this effective nuclear charge, which is increasing, is balanced by what? The electrostatic repulsion that is caused due to the addition of more and more electrons in the penultimate d orbital. Now electrons are having the same charge, they are negatively charged, so the electrons, they repel each other. Okay, so when we add more and more electrons into the d orbital as we are moving from left to right, due to the increase in number of electrons, there will be increased repulsion between the electrons. Okay, due to which what happens, the effective nuclear charge get compensated by this electron repulsion, and we do not observe what, a significant decrease in the size of the radii or atoms. Okay, this is why we observe what, almost copper constant sizes from this thing iron to copper. Now in zinc we observe what? A slight good increase in size. Okay, here the size is not decreasing. Why? Again here the electrostatic repulsion between electron is maximum, and effective nuclear charge have the d orbital is completely filled. There are 10 electrons. Okay, so the electron which is present in 4s orbital is shielded nicely by the d orbitals, and it has the biggest size. Okay, so you can generally just write that atomic and ionic radii decreases gradually from left to right. And if you want to this thing explain the particular behavior or the up rise and fall of the atomic sizes, you can give the reason which I have just mentioned. Okay, here in this diagram the green line is for the 3D series. You can see here that how the atomic radii starts decreasing from scandium to titanium, then vanadium, chromium, manganese, and till nickel it is decreasing, and zinc shows what? Increase in atomic radii. You can compare that and you can see that the same trend is followed in the 4D series as well as in the 5D series. Okay, that is the atomic sizes goes on decreasing when we move from left to right. That is, as the atomic number increases, the atomic sizes decreases. Okay, but in the end you will observe that all the series in the end the last elements shows increase in atomic sizes. Due to what? I've said that due to the shielding effect of the d orbitals. Okay, now we can study the this thing behavior or variation of this atomic sizes with respect to two different cases. Okay, number one is the element having the same oxidation state. It means when you move from scandium to zinc, you are doing what? You are observing the elements which are neutral, having zero oxidation state. And we have just discussed that when we move from scandium to zinc, how the atomic size vary. Okay, so this is the first case which we have already studied. The second case we can study is what? Considering various oxidation state of the same element, we can also observe the atomic or ionic radii, the variation in the atomic and ionic radii, when we can consider only a single element and its different oxidation state, and then these elements arranged in a series with their different ionic radii. Let's see. Now here I have shown what? When you go from up to down, this is your series scandium to zinc. Okay, here the atomic radii as well as the ionic radii in +2 and +3 states are mentioned. Okay, you can observe what? That let's see from vanadium, because scandium show only one oxidation state, titanium does not show +2 oxidation state. So let's see vanadium. In vanadium the ionic radii is 79 in +2 state and 64 in +3 state. So you can see that when the oxidation states increases, that is the charge on the metal increases, its ionic radius decreases, or its radius decreases or size decreases. Why this is happening? Because the effective nuclear charge increases. Now it is very simple. Just imagine that you had a nucleus, because look, when any element goes for ion formation, what happens there? There will be change in the number of electrons of that atom, but the number of proton never changes. It remains same in the center, that is in the nucleus. Okay, so in case of vanadium, we know that vanadium has 23 electron and 23 protons. The protons are in the nucleus. Okay, so when vanadium is in neutral atom state, the size of the, or the radius, atomic radius, is 135 picometer. Okay, when the vanadium is in +2 oxidation state, it means what happened, the 2 electrons are lost. Okay, now your nucleus have become more powerful because the number of protons are still same. It is still has 23 protons in the center, but the number of electrons are reduced now. +2 oxidation state means loss of 2 electrons. 2 electrons are gone now. Okay, so in +2 state, what happens, your nucleus becomes more powerful and the effective nuclear charge also becomes more powerful. Therefore the size decreases because now it can have more pull on the outer electrons. When you move from +2 to +3 oxidation state, the nucleus is becoming more and more powerful. Again, the number of protons are still 23, but the number of electrons have reduced to what, 20. Okay, so again the size will decrease. You can observe the same trend of decrease in ionic radii for all the different elements, chromium, manganese, whichever you want to take. Okay, so whenever the oxidation state of a metal increases, the ionic radii is going to decrease, and the reason is due to the increase in effective nuclear charge. Understood? These are some simple questions, students. Try to answer these questions to check your comprehension. Okay, many of these questions I have discussed. Okay, and these are generally based on the electronic configuration. In the same way, students, you may be simply just asked to write down about the trend of atomic and ionic radii in 3D series. Okay, that's it for today. Okay, be safe and study hard. Allah Hafiz.